All right, hello everybody, and welcome to our webinar today on low GWP refrigerants. We're excited to get into this important topic with you today. And we've got some great panelists here, which I'll introduce in just a minute to help us through this complicated but really important topic. You know, it's one of the things we don't think about a lot, but refrigerants are in a lot of products we use, from our refrigerators, of course, air conditioners. A lot of those devices you see in places like 7-Eleven, et cetera, they're storing keeping all our beverages cool, our cars and trucks, water heaters, as Joe just mentioned, more and more. And of course, heat pumps, critical to their function. So it's something that we need, but historically, the chemicals that make this all possible have high global warming potential, which means that when they escape into the atmosphere, they have climate harms that are far worse than carbon dioxide. And we'll get into all that. But the good news is that, you know, there are these global agreements that have been around for some time that demand that we transition to lower greenhouse gas global warming potential alternatives. And there's a lot of people who've been working hard to do this for a long time. We're going to be hear from two of them who've been involved in this for a long time and know more about it maybe than anyone that you're ever going to find, to help us talk about what this transition looks like, short-term as well as long-term. So I'm super excited to introduce our panelists. And we're going to be hearing first from Helen Walter Terranoni. Sorry for the stumble there. Helen, thank you. She's Director of Global Climate Policy at Trane Technologies. I'm sure you've heard of Trane. Anyone who's in the HVAC world knows that name. Helen has led transitions in technology, manufacturing, business, including low global warming potential refrigerant development, supply chain, environmental mitigation, hazardous process safety, and strategic planning. She is a co-chair of the UN Montreal Protocol Foams Technical Options Committee and member of the Technical and Economic Assessment Panel. She holds a master's degree in environmental engineering from Syracuse University. Thank you for joining us today, Helen. And we'll also be hearing from Christina Starr, who is senior manager at the Environmental Investigation Agency, EIA, not to be confused with the other EIA. Christina works in the EIA's climate campaign, which is focused on eliminating emissions of super pollutant fluorinated greenhouse gases, which is exactly what we're talking about today. And for the past decade, she's worked on the organization's investigative, corporate responsibility, and international and domestic climate policy work. She's been instrumental in driving HFC engagement with the U.S. federal government and in California, Washington, New York, and other states. So we're really thankful to have Helen and Christina with us. Just a little reminder, Helen is, we're fortunate to have her. She's traveling today. She's in the airport, so you might hear a little background noise from her, but we will work through that. So with that, I'm going to turn it over to you, Christina, to share your screen, and yeah, let's get into it.
Great. So Christina and I are here to talk with you all today about refrigerants and heat pumps. We hope that we're going to unlock some of your most pressing questions. First, we'll start by talking a little bit about decarbonizing the built environment, and then give a little bit of background on refrigerants. And then Christina is going to talk about a roadmap to climate-friendly cooling and heating. Christina, thanks. So my name is Helen Walter Terranoni, and I work for Trane Technologies on climate policy. So you can go to the next one, Christina. We'll talk a little bit about decarbonization. So for those of you who haven't been paying attention, sorry about the background sounds. Heating and cooling of buildings, we see emissions around 15%, and that's a significant portion of global emissions. If you add food loss and waste to that, we see about 10% of emissions. So in total, that's 25% of global emissions that we need to think about from the heating and cooling world. So the cold chains for food and pharmaceuticals, et cetera, is in addition to heating and cooling of buildings. So that's about a quarter of the pie. The next slide. So, you know, what does it mean to decarbonize? So there are direct emissions, you know, from things like leaks from refrigerants, refrigerant management, as well as electrification, so space and industrial heating. and then there are indirect emissions from the use of electricity from equipment, as well as other uses. And so if we think about the current state, and the direct emissions and indirect emissions and how they need to be reduced over time to the ideal future state, we at Trane Technologies, we have a 2030 goal, including a reduction of 1 gigaton of emissions from customers' buildings by 2030, as well as a long-term goal and a net zero goal by 2050 to support reduction of the increase in temperature globally to 1.5 degrees. So in the future state, we need to think about the net zero carbon electric grid, as well as reducing fossil fuel usage or eliminating, and also low GWP, low global warming potential refrigerants. So some of the things that we think about there are connected and real-time responsive buildings and homes. So some of the things that I follow very closely are policies related to energy and real-time understanding of the use of energy in buildings and its carbon footprint, so that demand can be shifted when possible to more renewable energy sources. You can go to the next one, Christina. Thank you. So some of the things that we think about are electrification of heating applications as a solution at a product level, as well as, like I mentioned before, refrigerant management. So reducing leaks, as well as the capture of refrigerants at the end of life. From the indirect emissions perspective, we think about building envelope improvements. So, a retrofit of a building may include additional insulation or better windows or lighting, in addition to reduce the demand for heating and cooling. That real-time electric demand that I talked about on the other slide, that will reduce energy waste, as well as increase the demand for renewable energy sources, and also reduce peak demand. So that reduces the amount of electricity that needs to be added to the grid long term. More energy efficient equipment and lighting will also reduce that demand and the need for more electricity generation, and on-site energy storage. So if you think about solar panels on a building, and then thermal energy storage to move demand across to times of day away from peak demand, or battery storage that can provide some resilience and flexibility and enhance the economic return of the on-site renewable energy production. So there certainly is a need to turn on the prediction of demand, as well as to facilitate generation and storage and ensure that supply meets demand. You can go to the next one. So we've talked through quite a bit of this. So again, we're just thinking about things at Trane Technologies from the product level, the building level, and the electric grid as all being equally important knobs to turn to reduce the carbon footprint of heating and cooling of buildings. You can go to the next slide, Christine. So now let's talk about refrigerants. So refrigerants include hydrofluorocarbons, and some of the uses that were noted earlier by Brian are included here. So if we think about retail food cases, so retail supermarket systems, or air conditioning in cars, or fire suppressants, some propellants, as well as meter-dose inhalers, and then air conditioning, as well as heat pumps, are all spaces that use fluorocarbon refrigerants in products. For those of you that are not familiar with the vapor compression cycle, I just wanted to kind of note here what's going on at the very basic level. So you've got this refrigerant fluid at a low pressure as a liquid. It's allowed to expand, and then it becomes a high pressure gas. And if you think about the expansion of a liquid to a gas, a great deal of you can feel a great deal of coolness down to minus 40 or 50 degrees, and as heat is absorbed by the refrigerant through that process. So I just wanted to make note of that as we think about that vapor compression cycle that is so important to refrigerants and heat pumps. In the case of heat pumps, the heat is expelled inside the house. In the case of refrigeration or air conditioning, the heat is expelled outside the house or outside the refrigeration unit. So that's just some basics. Christy, you can go. I'm just waiting to see who left their driver's license at security before I go on. So fluorocarbon policy has been ongoing for decades, since 1987 globally, when the Montreal Protocol for Substances that Deplete the Ozone Layer was agreed back in 1987. So back then, chlorofluorocarbons were the refrigerant of the day. They had extremely high GWPs, upward, in the thousands and even more than 10,000 global warming potential GWP. Over time, that's been reduced as we've gone through various transitions to hydrochlorofluorocarbons, which have generally been lower, as well as hydrofluorocarbons. And now we're looking at low global warming potential, low GWP blends. So more action that we have seen in the previous years. We have seen the transition from an HFC perspective. The U.S. EPA, the Environmental Protection Agency, has implemented in the 2015 timeframe significant new alternatives policy program, SNAP rules 20 and 21, which essentially bans certain refrigerants from use, higher global warming potential refrigerants from use. The Climate Alliance states shored that up when those regulations were litigated in the courts, and adopted those same regulations and bans in a dozen states. After that time frame, in 2020, the American Innovation and Manufacturing Act was enacted in December of that year, which also phases down the use of refrigerants. Since then, the U.S. has ratified the Kigali Amendment to the Montreal Protocol. So I'm going to talk more about these policies in a few minutes here, but what I wanted to kind of talk through is that these transitions are in place to reduce emissions due to losses during manufacture, installation, operation, servicing, failures, and end of life. And so if we didn't lose refrigerants by those means, these transitions would not be required. In addition, generally across this spectrum, the global warming potential, the GWP, and the climate impact has been reduced with every transition. And many products have shifted away from fluorocarbons through these transitions. So insulating foams from the transition from CFCs to HCFCs, there was a reduction of probably close to 60 or 70% of the use of fluorocarbons in that transition. So we've seen this happen in the past where it's been kind of a transition to other alternatives. Next slide, Christina.
Ellen, just a second on that last slide. It's fascinating to me. I didn't know that those CFCs, which we all knew were depleting the ozone, those actually had a higher global warming potential than. So we've already been stepping down our global warming potential from the 80s. Is that's the point?
No, that's exactly true, Joe. And in fact, some folks have said that the Montreal Protocol is actually the greatest climate treaty that's ever happened and been implemented because of because it's just been so impactful, and it happened so early on with these short-lived climate pollutants. So,
great, thanks.
So I'm going to back up a little bit and talk a little bit about how the Kigali Amendment to the Montreal Protocol. So like Joe said, the Montreal Protocol was focused on the ozone layer that protects us all from skin cancer. And it was amended in 2016 to phase down the supply of HFCs, so the production and the import of HFCs. And so it's quite a significant schedule. This is the schedule for the US here, with a 10% reduction that went into place in 2022, and a 40% reduction going into place in 2024. So next year, we're going to see a drop in the available HFCs by about a third. 2029, 70% reduction, and so on here. So there's the AIM Act includes a mandated phase down of the supply of HFCs, hydrofluorocarbons. It authorizes mandates around refrigerants. So what do I mean by that? It means that EPA can tell us to stop using certain refrigerants. They can ban some. They can set global warming potential limits. So that helps us to get a demand portfolio that matches the reduction in supply. Because if you don't have a match in supply and demand, then you see kind of crazy things happen in the market around pricing, as well as suddenly people don't have access to refrigerant and they don't know what to do. So in order to avoid that, EPA is trying to kind of balance things a little bit with these technology transition mandates. And in fact, their technology transition rule was just published last Friday. So we're going to talk a little bit about that. Separately from that, another way to reduce the demand of refrigerants is to manage refrigerants better. So stop the leaks, better servicing practices and so on, as well as the use of reclaimed refrigerant and better end-of-life collection practices, et cetera. And I did want to point out here, this is probably the most important point that I can make today, is that the success of this phase down depends on all stakeholders. So whether we're enabling the use of new refrigerants or kind of agreeing on when to make transitions happen and maybe even making them happen sooner rather than later, all of that, we all have to kind of work together on this interconnected system. Thanks, Christina. So the technology transition, the demand reduction side of things, that rule was just finalized on Friday. It was pre-published, and so that will be published in the Federal Register in the coming weeks. So here are the limitations that were set up. So in some cases, EPA banned certain refrigerants. In other cases, or other fluorocarbons, and in other cases, EPA set GWP limits. So you can see here, especially let's focus on air conditioning and heat pumps, since we're going to talk about heating as well, with a 700 global warming potential limit in 2025, and for variable refrigerant flow equipment in 2026. Sorry,
Helen, just to give people a little context of what that 700 number means compared to what we might be seeing today, or can you make a little comment on that?
So today, the most common refrigerant that's used in the US in air conditioning and heat pumps is R410A. It's a blend of R32 and R125. And the global warming potential of that refrigerant is 2088. So this is about a 2/3 reduction, versus what is used today. However, now I'm going to tell you a little bit of an insider information. The refrigerants of today, the 410A refrigerant of today, 50% R32, that's a lower flammability refrigerant. R125 is a fire suppressant. Those were added together, and that means that it was rated by ASHRAE as not propagating a flame, or in common layman's terms, probably being called non-flammable. So that designation will be different with the new refrigerants, and that's caused a lot of work to be done, a lot of research to make sure that this can be done safely, as well as a lot of work to be done to enable the use of these new refrigerants. And we're going to talk a little bit about that in the past 10 years worth of work to kind of get there. So I won't go through the whole details of that slide. Thanks, Christina, for moving on. But it is there in case anybody's interested in what those limits are. And certainly that can be found on the EPA's website. Separately from this, like I was just speaking about, these new refrigerants need to be enabled. So after these, or any technology needs to be enabled. So after a new technology is developed, safety standards must be updated and adopted. There are over 1,000 building code jurisdictions in the United States where their codes have to be updated to allow new refrigerants, or frankly, any new technology. Refrigerants have to be approved by the EPA SNAP program. So those have had to be approved by EPA. The Department of Transportation shipping requirements may need to be updated. And finally, equipment must be listed by nationally recognized testing laboratories. So NRTLs require the testing of energy efficiency as well as safety testing before they will list equipment as having successfully passed those tests. And energy efficiency is certainly dependent on the refrigerant, but also even more so dependent upon the design of the equipment. So compressor design, doors on refrigerator cases, foam insulation, and other things are very, very important features to energy efficiency. There's been a myriad of reports written by the EPA that talk about all those features. And if you even look at a Department of Energy rulemaking, they'll go into great detail about the contribution of those various design features that impact energy efficiency of equipment. So preparing for this pending transition, that's been underway for more than a decade. I would say probably 14 years ago, the industry started looking at new refrigerants and studying them and understanding their safety characteristics as well as other features, and kind of studying them in great detail, as well as looking at what would be required to enable their use. And that has been very important to set the industry up for success. Fortunately, the AIM Act schedule will also help to drive better refrigerant management practices, so leak reduction as well as better collection at end of life, and hopefully reduce the demand for fluorocarbon refrigerants further. So that schedule will do so, and better refrigerant management will help too. But again, the success of this phase down is really dependent on all stakeholders and everybody doing all the things that they need to do, and maybe even a little bit more. So, so certainly it's a united action that has to take place to kind of get this across the finish line. I think that's my last slide, Christina. So I think I'm heading over to you after this.
That's right. Here we go. Okay, so
Thanks,
guys,
Helen. Sorry, just before you jump in, I'm still like just getting my brain around this over 2,000 global warming potential down to 675. I mean, that's a really big jump. Yeah, I mean, I don't want to undersell that. It feels like that's a big step forward in the right direction. Yeah,
it's great. It's fantastic. We all want to go as far as we can, and certainly to move forward here, it's taken an awful lot of work. Like I said, you kind of had to take the fire suppressant out of that R410A to get to that alternative. And so a lot of work had to be done to kind of figure out how to do that safely. I mean, and Christina can tell you about this too. In olden days, folks used to use things like ammonia and propane and other refrigerants that we're looking at again today. But I think they didn't really understand some things about safety, and that kind of turned into some issues that drove, to kind of use fluorocarbons. And I think now people are studying safety very, very carefully and closely. And so I think it will allow for a broader array of refrigerants to be used as we kind of understand and implement safety features in equipment design and installation.
Yeah, and I'm going to talk a lot more about also the natural refrigerant alternatives, but I'm going to go through some of the things Helen has talked to, but more in the context of sort of where we are now and looking forward at the next decade in particular, of how we can kind of be on a path to get even more climate friendly in terms of our cooling. As Helen says, there's been a lot of work done already to get us to the place that we are now to make this possible. And there's a transition taking place that will significantly lessen the impact of heat pumps and air conditioners and other equipment. But we still have more work to do. So I'm going to talk a little bit more about that as well. So I think everybody knows this, but I just want to frame my presentation with, this being the critical decade for climate action, right? We want to cut emissions almost in half by 2030 and then achieve net zero by 2050. And when we think about this, it's important when we think about refrigeration and air conditioning equipment containing refrigerants, they stick around for 20 plus years. So the lifetime of different equipment can be quite lengthy. And so the things we install, today can be around and with us well into this time period of 2030, 2040 and beyond. So it's incredibly important that we transition as soon as possible to new refrigerants to avoid locking in emissions down the road while this equipment's being used. As we can't just drop in new refrigerants that have zero climate impacts, partly because of what Helen mentioned in that we have flammability and other things to deal with. So we need to actually design new equipment that can use these lower GWP or ultra low GWP refrigerants. So of course we use heating and cooling everywhere, as Helen has said, to make and store and transport and consume many vital consumer goods and to heat and cool ourselves. So we have these many different uses, and it's incredibly essential. And as cooling is essential already, as the world warms, it's becoming more essential. Of course, we are needing even more cooling, and the demand for cooling is going up very rapidly in our world, both as the climate warms and as certain countries reach, greater rates of people being able to afford air conditioners. So you can see right now through 2050, we're expected to be installing about 10 new air conditioners every second, and the energy demand is going to triple. We also will see, of course, an increase in the fluorinated refrigerants, as well as that goes up unless we transition. So again, in the context of refrigerants themselves, we have a big opportunity. This is why we worked so hard at the Kigali Amendment, which can avoid upwards of 0.5 degree Celsius this century by limiting these super potent gases that have global warming potential thousands of times as potent as carbon dioxide. You can see here on the right, without the Kigali Amendment, we would be facing incredibly rapid increase in the climate impacts of these gases. And as this global phase down comes into force, we will see this start to level off this decade and start to go down. This is incredibly important because these are short-lived climate pollutants, and so as we start to mitigate them, we see a really rapid result in terms of reduced warming in the atmosphere. But again, the long lifetime of equipment using HFCs means we need to act now to meet our net zero targets. And this is a phase down and not a phase out of HFCs. So we still have an installed base of HFCs and new HFCs being produced for quite some time under this agreement. In terms of the use by sectors, Helen talked about this a bit, but there are quite a few non-refrigerant uses. Those make up roughly about 20% of the HFC use. So the majority is refrigerants. And it's kind of roughly split between air conditioning, refrigeration, and motor vehicle air conditioning or transport. And we see about 65% of the refrigerant 40% of the refrigerant is for new equipment, but roughly 60% of it is for filling equipment. So this is to replace leaking refrigerants. There are quite a few leaks happening, which is also why this is so important that we reduce the leaks of the existing equipment. And in terms of this history of the Montreal Protocol, which again, Helen has touched on, we've been on this journey for decades now, right? There has been so much work and so much of a climate impact already from reducing CFCs and HCFCs and these ozone depleting substances, which had very potent climate warming impacts themselves. But now we have to implement this global phase down of HFCs. And we've been on a bit of a circular journey, right? Which is why I really like this diagram. Before we introduced synthetic fluorinated refrigerants, we were using natural refrigerants. There was a growing need for safety, and equipment wasn't being designed properly to be able to handle those either flammable or toxic natural refrigerants. And so CFCs were introduced to solve that problem. We then had the problem of ozone depletion, so we introduced a couple generations of new synthetic refrigerants, HCFCs, followed by HFCs, to reduce the ozone impacts. That had benefits for our climate, but was mainly in order to reduce the ozone impacts. And now we have a transition happening from HFCs to lower global warming potential HFCs, as well as a mix of kind of hydrofluoroolefins, which are very low global warming potential fluorinated refrigerants, as well as back to natural refrigerants. So we're on a journey that is in some ways taking us back to where we started, but in a very different time when we have much more modern equipment and much more modern safety designs and safety mitigation elements to deal with that.
Christina, while we're on the topic of the ozone layer for a moment, I mean, I know this is a little bit of a distraction maybe from a main conversation, but what's the news on the ozone layer? I mean, have our efforts been successful in solving that problem?
They have been quite successful. That's one of the reasons the Montreal Protocol is known as one of the most successful environmental treaties. The ozone layer is on a path to recovery by mid-century. There may be some things we can do to continue to speed up that recovery. You might see some headlines this year about there being a very large ozone hole, and that is because there was a very there are other things that impact the ozone layer in the short term, or the ozone hole in the short term, and there was a very large volcanic eruption that has caused a bigger ozone hole this year. So don't let that make you think we don't have a successful ozone recovery. We do, and we are on the path to the ozone layer recovering fully by mid-century.
Thank you.
Yeah, sure. So now I'm going to talk a little bit more. I know folks are interested to understand some of the differences between natural refrigerants versus HFCs and HFOs. So I think one thing that a lot of people don't understand is that a lot of the new refrigerants we're introducing are actually blends of HFCs and HFOs. So we're taking the higher GWP substances and mixing them with lower GWP substances, and coming out with blends that are mildly flammable, in many cases A2L, which are being enabled. So we have a mixing of these two things. But in some cases, we also have pure HFO refrigerants, which have very low GWP. So an HFO might have a GWP of 1, and an HFC might have a GWP of, you know, thousands. And then when you mix those together, you end up with this kind of lower global warming potential. When we talk about measuring global warming potential with HFCs and HFOs, we should be looking at the 20-year global warming potential. As I mentioned, these are short-lived climate pollutants. And when we really want to account for what their actual impact is, the 20-year period is sort of the most appropriate thing to look at. Now, we use the 100-year global warming potential when we talk about bans and other things for policy reasons. But if we're interested in accounting for what the actual impacts are, the 20-year is the most relevant. So you can see even some of these lower GWP HFC, HFO blends, such as 449A, you know, R32, even though their 100-year GWP might be, say, 600 or 700, their 20-year GWP is still in the thousands. So these refrigerants still have quite a significant climate impact. And in particular, when you compare them with natural refrigerants, which ammonia, carbon dioxide, and some hydrocarbons, which all have what we would refer to as ultra low GWPs, less than 5, as do the pure HFOs. So we really have a significant difference still between these HFC, HFO blends and between natural refrigerants or pure HFOs. But unfortunately, there are some other issues with HFO substitutes. One of them is that according to certain definitions, they are categorized as PFAS, or polyfluoroalkyl substances, or forever chemicals is what they're often known as. And this is a group of thousands of chemicals that can break down and be either persistent in the environment or bioaccumulate in humans and animals. And in the case of HFOs in particular, they break down into some short chain PFAS molecules, and trifluoroacetic acid is the one that we're the most concerned about, because HFOs produce a lot more of this TFA than HFCs did. So we see from HFO 1,2,3,4-YF, which is the most common HFO in a lot of these refrigerant blends, more than a 30-fold increase in the amount of TFA being produced. And so scientists are seeing the rising levels of this TFA in the environment, in ice cores. They can see the trends already increasing, and a number of studies are seeing this. So the question really is now, how much of an impact will this have in the future? But there's quite a bit of reason to be concerned and be keeping tabs on this. So as a result of this, the European Union, as well as some US states, are looking at PFAS regulations that would also regulate HFOs. The other issue with synthetic refrigerants, including HFOs, is that an HFO might have a GWP of 1, but in order to produce that HFO, we had to use a number of what we'd call feedstocks, chemical feedstocks, which include high global warming potential. ozone-depleting substances, and that there can be byproducts of that production process, including a very high global warming potential substance called HFC 23. And so we've seen rising emissions of some of these byproducts and feedstocks in the atmosphere. So recent scientific studies show that this may be contributing about 860 million metric tons of CO2 annually when we add up all these different emissions of substances that come from the production of fluorochemicals or are linked to the production of fluorochemicals. For reference, that amount is about the annual emissions of Germany. So that's not an insignificant impact that the production of these chemicals is having on the climate. So a little more on the natural refrigerants or non-PFAS refrigerants, if you prefer that nomenclature. There are, as you can see on the right-hand side here, there are a lot of refrigerant blends that are HFCs or HFOs that may have GWPs, ranging from thousands to hundreds. But there are really only a few substances that have both ultra low global warming potentials as well as are PFAS free. And those are the so-called natural refrigerants or non-synthetic refrigerants. And that includes R744, which is carbon dioxide, R290, which is propane, and R717, which is ammonia. And there are also a few other hydrocarbons as well, R600A isobutane, which is now being used in all new household refrigerators, for example. And some of these are already being used in quite a few types of equipment, while other sectors still have yet to have much use of natural refrigerants. So I'll talk a little bit more about, some of what are the alternatives available in terms of the sectors. Where do we see natural refrigerants being used versus not? And essentially, we see that across the refrigeration side of things, we see quite a bit of availability of natural refrigerant equipment. Supermarkets, for example, and food retail applications have a lot of CO2 systems, as well as hydrocarbons being used in self-contained refrigeration equipment, like your beverage coolers and display cases. Transport refrigerant, ice rinks, household refrigerators. A lot of this equipment is already transitioning to natural refrigerants. Whereas in the heat pumps and air conditioning sector, and this is reflected by the 700 GWP that's been applied in the EPA regulations, we don't have as much availability here, especially in the US, of natural refrigerants for these uses. So Helen talked a lot about all the work that's been done to enable the more flammable HFC, HFO blends, and there would need to be further work done in order to enable hydrocarbons in this sector, which would be an available alternative for heat pumps and air conditioners to be both ultra low GWP and PFAS free.
Christina, could we just, that's a great point. Maybe so we could have a long discussion on this, but the fact that natural refrigerants aren't available for heat pumps and air conditioners, is there, I think there's some, we saw in the chat, potential conspiracy theories on, because it's not patentable, these, that companies prefer these HFOs because they can make more money on them, or is it flammability? Could you speak to both of those and talk to us?
Maybe I can afterwards.
Yeah, both. Yeah, please comment on why we haven't seen a more rapid adoption of natural refrigerants in heat pumps.
It's very true, Joe. They are non-patented substances, so you don't have a big natural refrigerant lobbying for them. That may be true, but I'm not going to go into conspiracy theories, but I think there has been a lot more focus here in the US on the synthetic alternatives. There is a little more availability of naturals in this equipment in Europe and elsewhere, and particular some types of equipment that I want to talk more about in terms of like heat pump water heaters, for example, or air to water heat pumps. So yes, there is a difference in terms of the business models, but I think equipment manufacturers don't care what refrigerant they're using. They don't profit from refrigerant. And so I don't know if this is what Helen wants to talk about,
yeah.
but I'll let her chime in.
Yeah, no, if I can avoid some announcements here. No, I mean, we at Train Technologies, we don't make refrigerants. We don't care what the I mean, like we don't, from that perspective, like we don't care what the refrigerant is. We are interested in, how can we, meet our gigaton challenge, reduce that, those CO2 equivalent emissions. We're trying to look at, a lot of different things, certainly EPA does when they're looking at new refrigerants. They look at a lot of different things. They look at toxicity. They look at things like safety and so on and so forth. But one of the things that we look at as we look at new refrigerants is kind of balancing direct and indirect emissions. And I have been kind of watching in the chat. Propane is a very efficient refrigerant in many cases. So Christina and I are not here to argue against its use. From the perspective in the US, we've just gotten these lower flammability refrigerants across the line from a safety standard perspective and now into the building codes. And I feel like someone owes me 5 years of my life back for all the work that I had to do to get this far. We'll have to see what it's going to take. They're not really in the safety standards sufficiently yet to even be adopted in the building code. So, I know Christina sits in those safety standard meetings and, and we have folks at our company that sit in those groups, and we're certainly looking at, what's going to be needed to move additional options forward. We want everything on the table, right?
So
sorry, maybe just to like build on that, because the safety thing for a second, just to make sure everyone understand what we're talking about here. The way I understand it is that building codes across the United States would not let you use propane as a refrigerant because of its flammability, worried about explosions, that kind of thing, which is a little bit like mind-blowing considering that they have no problem with you pumping that into your house, to like use your stove or something like that. But anyway, the point is that building codes today do not support the use of many of these alternatives we're talking about, potentially even ammonia. I'm not sure, but is that so that's part of the problem is the building codes have to change along with the refrigerant change.
Yeah, go ahead, Christina, then I'll chime in.
I was going to say ammonia is allowed in building codes in a lot of more industrial uses, for example, and ice hockey rinks use ammonia in a lot of ice hockey rinks. It's the most common refrigerant. About 70% of ice hockey rinks in North America use ammonia. So there are codes when you use it in a machine room. There's just conditions on how to use it that have been put in place for many years. Ammonia is not approved for any kind of residential or occupancy or where it would be in an occupied space. And so the same, and it's a matter of doing the work to make sure that if there is a leak of refrigerant, whatever refrigerant we're talking about, right, there can be safety issues with any refrigerant, even if it's not flammability, a non-flammable HFC, if it leaks enough into a room, it can displace oxygen and a person can suffocate because of it. So it's just different risks that we need to manage for different refrigerants. And all the work that has gone into that Helen has done has been enabling these A2L refrigerants. So we can get a 2/3 reduction, in the near term in our climate impact in this AC and heat pump space, in the next couple of years here, transition. In the meantime, that process would need to be expanded to look at the hydrocarbons in order to enable that. So I have a couple slides on that if you're interested, and I can talk more about what that would look like. Yeah.
Maybe I can jump in a little bit. So on the propane side of things, it's been estimated that about $10 million has been spent on research on flammable refrigerants. And one of the projects that was done was actually, I think there have been two now, is to look at odorant to be added to different refrigerants. So, if you think about propane that's used to heat people's homes or natural gas or what have you, they add mercaptans so that if there's a leak, you can smell it. But unfortunately, an odorant fouls the heat exchanger in an air conditioner or a heat pump. And so it's problematic, to add an odorant. And so unfortunately, these systems, do see leaks from these systems. Otherwise, we wouldn't even be having this conversation about refrigerants. And so, there are questions around, well, what's a different thing that we could do instead of adding odorant? Like, how can we achieve the same level of safety in a different way. And those are the conversations that are happening at those safety standard meetings where Christina's attending and my colleagues are there, kind of talking through, okay, well, what else can we do, right? And then I also saw a question in the chat around, kind of using the term natural to describe these refrigerants. It's kind of a slangy term. It doesn't mean that like somebody's, scooping it off a tree or something. It just means that it does exist in nature, right? So I recognize that it's kind of a slangy term, but it is kind of fairly commonly used. So, Christina and I, we're not trying to be loosey-goosey with it, but it is pretty common that it's used. So.
Yeah, it's a natural molecule as opposed to a synthetic molecule. So it exists in nature versus the fluorinated molecules had to be engineered, and that's why they're patented, in fact. So yeah, I'm going to go a little more into what this might look like and why it's important that we continue to look for another transition in the AC and heat pump sector. So this is a graph showing what's happening with the split AC heat pump sector globally. On the left, you see the stock of units increasing as demand grows this century exponentially. And on the right here, you see what's happening with refrigerant emissions. And the baseline here in black is the business as usual if we were not phasing down HFCs. The orange is what we're basically starting to do under the new refrigerant regulations, introducing HFC 32 and other similar, what we'd call mid-GWP refrigerants. And then this blue is what would happen if we rapidly introduced propane or some other ultra low GWP refrigerant in this sector. So you can see there's still a really significant mitigation potential here for this sector, and especially because of how quickly it's growing. So how would we accomplish this? How would we make this equipment available here in the US? Well, I want to say there's a couple of key safety standard organizations that do this work. And in fact, there is an international safety standard under the IEC, which is the International Electrotechnical Commission. And in that safety standard, it has now enabled the use of hydrocarbons up to a kilogram, 988 grams of R290 propane in a sort of split heat, air conditioner or heat pump. And then the charge size is greater than that if we're talking about using it in an out where the refrigerant is isolated outdoors. It's up to 5 kilograms of R290. So we have international safety standards that do allow the use of hydrocarbons already. And as a result, we have seen more introduction of this equipment in Europe, as I've mentioned. Unfortunately, US safety standards in particular have not been updated and are a bit outdated in this respect. So this needs to be a big area of focus going forward to essentially harmonize these US safety standards with international standards. So this UL 60335-2-40 standard, UL stands for Underwriters Laboratories, which is one of the product safety listing organizations. This standard restricts R290 to 114 grams, which is, a very minute amount, and it is not enough to design any kind of equipment with. You can't even design a small window air conditioning unit with this much refrigerant, right? So this restriction just simply doesn't allow for design of equipment in any kind of cost-effective or energy-efficient way. So we really need to focus on this and what this product looks like. Fortunately, I see a lot of good progress happening here already. There's some work being done by the ASHRAE 15.2 committee to enable hydrocarbons in what we'd call indirect outdoor systems, monoblocks or these kinds of units that would sit outside. The hydrocarbon refrigerant would be isolated to a self-contained system outdoors and would be heating and cooling water for the indoor space. So, these types of units have been on the market already in Europe for some time, and we're seeing a lot more manufacturers coming out with these types of units. I think anticipating that this is a growing market. And this is an application where propane is particularly good, thermally suited for this application of heating water to high temperatures. So it's one where it's also by far, I think, the most optimal refrigerant solution for this use. So there is a proposal here, and if that proceeds in a timely way, it would then need, I'll go through what the process would be after that, but it would still need to be approved by the EPA and go through several other steps in terms of building codes. But in the meantime, there's still a whole range of other types of equipment, right, where propane is still blocked. And so we really need to cover look at how we can enable propane safely in self-contained air conditioners and heat pumps, as well as potentially split and ducted systems, which are ducted units in particular, which are more unique to the US market. And we don't see that equipment, in other places.
Sorry, Christina, can I just interject here just to make sure I understand? So with the scenarios on the left, the reason why that is possible is because basically all the quote unquote dangerous substances are outside the home, and we're transporting water back and forth between the external unit where the heat exchanging happens and the on the outside in the internal spaces where we're either radiating that heat or whatever. So all the dangerous stuff's outside. And then on the one on the solutions on the right, or the scenarios on the right, we're talking about that's where the safety rules would have to change in order for us to be able to use these kind of systems in a way that would match with what the international standards say is acceptable.
Well, actually, both of these the standards need to change to enable either the outdoor use or the indoor use. The difference is there's already a proposal being worked on for the outdoor use here in the US. So this is in progress. There are experts discussing this right now. It's in progress. People who are interested should engage in that process. They can comment. It's been open to stakeholder comments. And the difference is, yes, the outdoor use means that if there's a leak, if the refrigerant leaks out of the system, it's going to be installed such that that refrigerant is going to stay outside and it's going to dissipate very quickly. You're not going to get a flammable concentration that gets trapped somewhere.
Gotcha.
When we talk about indoor installation, we have to manage for those scenarios where there's a leak inside. And so typically we design these maximum flammable charge sizes so that if there is a leak, and there could be a flammable concentration that could form inside the occupied space of a home or a building, that we'd have some kind of mitigation element that would prevent that from happening. It could be a fan kicking on. It could be a sensor that detects the refrigerant leak and shuts it down such that the leak can't enter the space anymore. There's different things that these standards require in the design of the equipment that would still prevent that from happening, but it needs, more thoughtfulness and more work to deal with that risk of the indoor space.
Gotcha.
But the idea of these safety standards is we're going to create equipment that is going to have no additional flammability risk from the equipment we have now, even though it's going to contain a flammable substance.
So one last question on this. I mean, is in terms of these safety standards, is there I think a lot of us in this environmental space are used to organized opposition to policies that are kind of pretty essential and to hit our climate goals. Is there organized resistance to these safety standards being changed? I mean, in the same way that we see around other issues, or is it just more that we're just haven't been paying attention to this enough?
I think it's more the latter. I don't think it's an organized resistance. I think you do see it's a bit of a black box, these standards processes. So it can be, sometimes I think we do see the safety stuff being over exaggerated for the interests of folks that might want to see, other refrigerants be used more. I would lie if I haven't seen that happen. But at the same time, I don't think it's an organized resistance. I think it's more about educating folks on what we're really talking about here. Especially when it comes to the firefighters and local building code officials. They have to accept these new standards, right? So we need to educate them on what this really means and why this isn't going to be a much greater risk to people as well as to first responders in the case of a fire. And as I'm going to show on the next slide, it's also because there are a lot of steps involved in our refrigerant approval process. So I just love to show this diagram, even though I'm not going to walk through every step in it, but it starts with this product listing standard, right? Typically, as well as an ASHRAE 15 standard. So these two blue boxes on the left, both of those are going to need to be updated if we're going to enable propane in this equipment. So that's two different standards committees that need to discuss and align themselves over what, the requirements will be both for the product itself, as well as what are the requirements for where and when it's installed. Then we need the EPA to snap approve that refrigerant. And the EPA will look at those safety standards and make a determination of whether, it agrees with what those conditions are for the safe use of the refrigerant. They might add some additional safety requirements on top of that if they feel it's needed. And then we have the building code process, which in the United States, we have both these model code organizations, the ICC and the IATMO, which create model codes that are then adopted on a state and local basis. So every state has some version of the ICC or the IATMO code adopted, but they may be years before and operating on a version of that code from 5 or 8 years ago in many cases. And so getting those 50 states to adopt new building codes is by far, I think, one of the biggest hurdles to this transition. And Helen can tell you a lot more about
Oh my God,
that.
I can't even tell you the blood, sweat, and lots of tears. And there are 1,000 building code jurisdictions, over 1,000 in the U.S. Like some states don't have statewide codes. Like there are 60 something in Colorado. It's in Texas doesn't have state. It's a lot of work, and it's not familiar work to this space. Like this, we're not used to having to do this to enable new refrigerants. So it's been a lot of work, and you can see this work, and it's yeah. So it's when we think about like those policies where, Brian, you're kind of talking about like opposition to climate policies. There are two work streams that I think about, and Christina probably does as well, when I think about making these transitions happen. And this is also for heat pumps. We have to enable things like somebody in the chat was talking about issues around the interoperability of the grid with like microgrids. So, geez, I've got solar panels on my house, or how do I get that to kind of operate better with the macro grid? And I think that I think that those are the kind of policies that enable transitions, right? So that we can use more renewable energy. This kind of work that Christina's talking about, where I still want 5 years of my life back on this, Christina probably does too. These are the things that need to get done to enable new technologies. And when we think about like banning things, like that's a little bit easier to think about, but we've got to think about also how to enable things. And there's a lot of like, put your nose to the grindstone, or I don't know, shoulder to the wheel, or whatever analogy you want to use to kind of get all this stuff done.
Yeah, and I see a question in the chat about the timeline for outdoor 5 kilograms of R290 to be fully legal in the US. And I will be speculating if I even say this, but I think it's doable this decade. It's doable. Like I said, I think we want to be on a I think this will be sooner. This will be the stepping stone. And by the end of this decade, we'd like to see this whole sector transition to ultra low GWP. But what do you think, Helen? A few years, we could have an EPA SNAP approved?
My hope, Christina, is that it's going to kind of flow through that ASHRAE process, and we're going to see it kind of move forward, and then EPA will kind of do its part, and we'll move forward, right? But even if we had kind of a straight shot and we didn't really know what we were doing. If we'd have a straight line shot, we might have carved 3 or 4 years off. But it's definitely a time-consuming, laborious process.
Yeah, one thing we learned in this process, I think, was ways to get it done faster, even while the model codes are still being updated. A lot of states have adopted legislation now saying that once EPA approves a substitute, that the building code in that state or in a local jurisdiction shouldn't block that refrigerant.
That's great.
So I think for that reason, we could see an easier pathway. I have this 7 to 10 year range here at the bottom of this line for how long this all takes. It can take that long, but I think it can also be faster, especially in the case of this new proposal. So there is hope for this to happen faster.
The other thing that I think is happening, Christina, well, I work for a big company, so I guess I shouldn't say that. I mean, I think some companies are looking at lots of different solutions, but maybe smaller companies are kind of still getting their arms around this current transition. So I guess I should say.
Yeah. A
Yeah.
lot of companies are looking at how to meet their 2030 and their 2050 targets, right? And it's almost as though their climate targets are a bigger driver in some cases than, say EPA regulations or the HFC phase down.
Well, let's run through the remainder slides, and I think we have a couple of questions. I know this has been a great discussion.
Yeah, it's been great.
Yeah, I'm
Ju-
going to just talk a little
Yeah,
bit
go ahead.
about life cycle refrigerant management, which is often the forgotten stepchild of the refrigerant discussion, but incredibly important. And so this is like the third leg of the stool when we talk about the refrigerant phase down. And fortunately, it will be a major focus of EPA regulations. One of the regulations that just came out on Friday, along with the technology transitions that we talked about, is a regulation to reduce leaks and increase the reclamation of refrigerant at end of life. And so that is something where we have a really big opportunity, because there's already so many refrigerants out there in our installed equipment, as well as that will still be produced. Unfortunately, most of the refrigerant, particularly at end of life, is being vented, right? We don't have a sustainable life cycle management ecosystem in place. And it's a challenge globally, but it's also really a challenge here in the US. We estimate that less than 20% of refrigerant is being recovered at end of life. So unfortunately, most of it is being emitted. And there are a lot of opportunities here to encourage this more sustainable practices, especially in the contractor and technician space. And in the whole kind of what we call like creating a reverse supply chain for refrigerant at end of life. And there's different policy mechanisms we can use to encourage this this increased recovery, reclamation, and destruction of refrigerant at end of life. But one of them we're particularly excited about that we see in the proposed EPA regulation is requiring the use of reclaimed refrigerant for new or existing equipment, as well as kind of procurement initiatives to use reclaimed refrigerant. So we see an initial proposal from the EPA that actually would require broad swaths of new equipment to potentially use only reclaimed refrigerant if it's still using an HFC beginning in 2028. And essentially what that could do is sort of drive more of what we would see as a best practice, best case scenario in refrigerant life cycle. And so what we need to encourage and incentivize happening is that technicians will actually recover and collect refrigerant, be able to take it back to a distributor of refrigerant and return it to them. That recovered used refrigerant is getting consolidated and transported and taken back to a facility, EPA certified reclamation facility, where it can be reclaimed, reused, and then used to service equipment. This is also really helpful for the phase down, because we have a lot of equipment that is designed to still use HFCs. And so if we have a shortage of refrigerant, having a sustainable source of reclaimed refrigerant can help us ensure there's a sustainable supply still that is not requiring new production.
I mean, Christina, I think I've been hearing sort of anecdotally, but chime in, and Helen, you would have good perspective on this too. But it feels like I've been hearing anecdotally that the installers are being advised to be really good in the short term here at reclaiming 410A, because people are worried about there isn't going to be a good supply of that out there to maintain systems that are in the field now. So one, my question is, am I correct on that? And two, that would seem like a good thing, that basically this sort of fear of a shortage of 410A might be actually prompting some better behavior on the standpoint of how we operate in the field with the existing systems. Is that what do you guys say about that?
Brian, I think that like this is a really it's Christina and both of our secret obsession, right? We both think it's an orphan policy gap. Christina, I'm speaking for you, but you and I have talked about this so much and spent so much time on this. I did a survey with contractors and other stakeholders in this space, and at first they were telling me, oh, why don't why doesn't the guy recover refrigerant at the end of life? We didn't say, why don't you do it? Why doesn't the guy recover refrigerant? And that first thing people started to answer, oh, we don't get paid enough. Oh, we have to pay when we drop it off. But then people started to answer, my equipment isn't fast enough and it takes too much time. And so I think that we really need to, as an ecosystem, kind of dig into this question and try to figure out, like, what are the barriers and how do we help people fix them? People tend to do, we need to make it easy to do the right thing and hard to do the wrong thing. And I'm afraid that we're in the opposite situation right now. So I don't know, Christina, what your thoughts are.
Yeah, no, I totally agree. I think the incentives need to be there. The guys servicing your residential household air conditioner are overworked, underpaid. They're very busy. They don't have time to think about the climate benefits of this, right? They just want to get to their next job, especially in high season, when everyone's air conditioners are breaking, right? There needs to be an incentive for them where it actually hits their bottom line, that if they return that refrigerant back to their distributor, they're going to get rewarded for that financially. There's just no other way about it, I think. And so I think we need to put the right kind of product stewardship system in place where we make sure those incentives are there. People have talked about deposit refunds, schemes that some European countries have those. There's an extended producer responsibility scheme in Australia where there are rebates for technicians, things like that. So we think a lot about what are those kind of systems we can put in place to create a sustainable mechanism to incentivize this.
That's great. And maybe a quick follow-up. So people have been asking a little bit, well, as we're going to this new phase of lower GWP refrigerants, should I hold off on buying, equipment that uses R410A? Any thoughts on that?
I think that, oh, sorry, was somebody going to say something? I don't want to interrupt.
No, go for it.
Oh, no, I was just going to say, like, I think, okay, you could say, well, let me look at my grid and the plan around my community for my grid. Where do I live? Do I live in a small space or a big space? I think there are a couple of elements to it, but I wouldn't hold off over the refrigerant. I think that when we look at the overarching scope 1, 2, 3 emissions in our space, the emissions related to energy are overarchingly, scope 3 emissions, are overarchingly predominant. And heat pumps do have the benefit of energy efficiency, and so maybe it's a little bit of a unique answer for folks, but I don't think that this should be the reason to hold off. I know, Christina, what do you think?
Don't wait. Ask your supplier if they can give you an R32 or a lower GWP heat pump, right? Ask them if they have that available now. And depending on where you are in the country, you may be able to already install a lower GWP piece of equipment quite soon, right, Helen? And so do that, demand that. But most people are not don't have the luxury to wait years to replace their boiler or replace their furnace, and they're incredibly urgent. And so I think don't wait for the refrigerant transition to be perfect and done. I think it's important that the industry does this as quickly as possible in the coming years, but we can't wait to scale up heat pumps. And at a household level, the best time to buy a heat pump is now, really.
Yeah, or 2 years ago. Yeah,
don't wait. I just flipped to the screen because that was one of my points. Yeah.
Yeah, I just want to drive that home because all the science says that even with the leakage that can be expected from these systems today, with the refrigerants we have today, let alone the next wave, that they're vastly better than heating our homes with fossil fuels. So I just want to put a point on that. But yeah, sorry, Christina, do you want to sum us up here?
Yeah, no, so I just wanted to kind of give my wish list for what we need to do by 2030. If by 2030 we can reach, ultra low GWP, PFAS-free alternatives for these applications that have reasonably good and improved energy efficiency, I think that puts us in a really good position to meet our, net zero 2050 targets, right? So we're already reducing the impact of refrigerants, and we need to remove some of these barriers and the safety standards and codes, keep buying heat pumps. We need to increase the recovery and reclamation at end of life. And we need to ultimately do what we can to accelerate the HFC phase down, both globally and here in the US. The Montreal Protocol has this history that maybe we didn't go into enough, but it's always been a start and strengthen treaty where it starts a phased out or a phase down, and then it sort of accelerates that based on, how the implementation is going. And I think we'll see, hopefully here in coming years, incredible that we're going faster than we think we are, especially if we can scale up the availability of reclaimed refrigerant to meet our market needs. And so I think we could see ourselves ready, in the coming years, if all goes well, for an acceleration to this HFC phase down.
That's fantastic. One question I have for you both is if either of you have examples of model policies that you think are worthy of replication at the state level or whatever around incentives for recovery. I know there's some policy folks who will be listening in on this, and I would love to be able to, just spread the word on that. If you have some.
Can I tell you my secret wish on this, Brian? I would love to get an intern going to look at a couple of different solutions in different locations. So what if you had like a library box drop off used refrigerant, right? So that the contractor doesn't have to drive 40 minutes to go drop off refrigerant. Like, try that out. Would that be the easy thing to do that would get people to do the right thing? I think that we need to really try some really novel and probably wacky ideas to try to get this done. There's a group in New York in the Hudson Valley that actually goes to landfills and collects refrigerants from like small units and refrigerators, because that's a fun thing to do on a Saturday. So those little novel things to try, I think would be great. And then to share that information, across the ecosystem, might help us to kind of figure out what the answers are. Because if we had the answers, I'll tell you, Christina and I would be sure to share them.
I would love to see a couple of states in the coming years pass pilot extended producer responsibility schemes. This is the type of model that we've seen in place in some other countries where, and it's been applied to a lot of other products like batteries, carpets, you name it. A lot of states have passed EPR programs for creating a better end-of-life management of other goods. So I think we need to apply that model to refrigerants. There are some things that are going to be unique about refrigerants, but we should pilot it at least and see if we can work out the kinks and get it to work well, to bring up those recovery rates, and set actual targets for how much we would like to be recovering, right? So there's certainly anyone interested in that, I'm happy to talk more. Certainly some thinking and work in the works on that.
Great. Hey, there's a couple questions. I know we are over time. Maybe we could do these. I have a couple questions on my list we could do quickly, potentially. We'll see. One person was asking about zero refrigerant solutions. What are the state? What's the state of research into thermoacoustic refrigeration that potentially would use zero refrigerants? Any comments there?
I think there are companies looking at everything. So I wouldn't, I can't talk to you about our research, our innovation program, but I think there are companies looking at everything.
Okay.
Yeah, there's a few different, there's magnetocaloric, I know magnetocaloric, there have been actual sort of smaller appliances are seem to be the best application for that. I think that might be the space to watch for the first kind of what we'd call non-vapor compression technology to hit the market, but we're still some years out from any of that equipment becoming commercially available, I think. So it's simply not going to happen it seems that it's not going to happen on a timeline that will be, compatible with meeting our climate goals. So we do need to kind of work on the refrigerants themselves, while also encouraging that technology where it's available. Yeah.
So I have a question that sort of I've been burning to ask, because I'm sure that with this transition that's right in front of us, and because the timeline is 2023, right, to phase out of 410A. Is it the end of 2023?
It's 2025,
24. Yep.
right?
Yep.
Okay.
24,
26.
25. Yeah.
All right. So we're in the middle of this transition. I mean, oftentimes people have anxieties that this is going to cause like hiccups in supply chain. You know, it means that I'm going to order a heat pump and I'm going to be able to get one because of the shortage of this new refrigerants or whatever, or the equipment. Can you guys just give us a comment on whether you have any anxieties about that? Is that keeping you up at night that we're going to incur some kind of rocky transition here?
I think people have been working toward this for 10 years, Brian. And I think, companies have kind of built out their plans and they're refining them. Now that they've seen the final regulation out the door on Friday, they're refining their plans to make sure that they're going to be compliant and ready with equipment available. So I've seen a lot of effort, when I worked with the industry association, it's kind of by many companies to try to be ready for this.
Great.
Are either of you worried about an unintended consequence of having to increase the quantity of refrigerant in these HFOs compared to, so maybe, nominally they have less global warming potential, but then you have to use a lot more of them in machines because they weren't.
I mean, I think, when I looked at Australia a couple of years ago and, with their transition, because you took the fire suppressant out of the refrigerant, it was a little bit more efficient. So you could use less. Now, energy efficiency, you need a little bit more. Heat pumps, you need a little more. Does it all come out in the wash? Maybe it's not perfect, but it's pretty close. And I'm not super panicked about that. And I think also, hopefully people are going to be very focused on leak reduction and, looking at technologies to do that so that that reduces the need for more refrigerant as well as the other refrigerant management practices, Joe.
Okay.
Yeah, I have some questions about some technologies. I'll name one: variable refrigerant flow. These types of heat pumps that actually use quite a significant quantity more refrigerant than other designs. I think it'll be interesting to see, since we do have the limits on the refrigerant, those types of equipment may need to become more efficient in how they use refrigerant while trying to deliver energy benefit, maximum energy efficiency. So where the market comes out on how equipment is designed will be quite interesting. Will we see equipment get designed to be more efficient with refrigerants? I think that's possible, especially the proposal that EPA just came out with on Friday on refrigerant management for leak management. Previously, any kind of system under 50 pounds has been exempt from any kind of refrigerant leak regulations under federally. But the proposal from EPA is to expand that to any equipment over 15 pounds, which will be quite interesting because there's a range of kind of more commercial, let's say commercial air conditioning equipment that may now be subject to leak regulations. And so as Helen says, if we get a lot more efficient with how we design equipment to be more leak tight, as well as, prevent and detect the leaks sooner, we could significantly reduce the amount of refrigerant we're using that way. As I sort of showed in one of my earlier slides, I think it's something like 60% of the refrigerant use is actually to refill and replace leaks. So that's a big amount that we can reduce that way.
Wow. Great. Brian, any last questions? We're a little.
No, I think we should probably wrap up. I mean, this has been such a fantastic and fascinating topic.
Maybe there was a lot of worrying questions. I think people being worried about a nefarious plot about new refrigerants, but I hope that Christina kind of dispelled some of that. We just need to enable them, and then people there will be more uptake of them. So, I don't think that there's some R32. I don't think there's a patent on the actual refrigerant. There may be on some of the technologies, R454B and other refrigerants. Maybe there's some patents, but at the end of the day, companies are looking for best solutions, and so we're not all, we're going to innovate and we're going to go and find what's best. So I wouldn't worry about folks trying to throw a wrench in the monkey works. I mean, we've overcome whatever was in our way around this generation of refrigerants, and if we have to overcome it again, then that's what we'll do, right, Christina?
Yeah.
Just be another 5 years of your life, Helen. And
well, I guess I come away from this conversation excited about the transitions that are right around the corner in terms of what impact those are going to have, and also excited about the fact that there seem to be known solutions that are out there, lots of problems to work through, but also, you know, some known solutions that look really encouraging. And I'm also would say I come away from this very thankful that there are people like you who are working hard on this, because I do appreciate this incredible amount of bureaucracy has to be like aligned and organized in the right way to make these things happen. So thank you both so much for the work that you're doing in this space. I mean, it's unbelievable. I know some of this behind the scenes stuff that's just makes the world so much better. So thank you both for your work, and thank you for helping us out today to explain this to everyone. This is a complicated topic. But yeah, I think we should wrap up. Joe, do you have any other thoughts maybe?
No, we'll send slides and recording out as soon as we can, probably tomorrow at the latest. And yeah, we just huge thanks to Christine and Helen. This has been a fascinating conversation. I've learned so much. I hope you all have as well. So we'll leave you with our usual slogan. Brian, go ahead.
Yeah, so thank you all for tuning in, and good luck with all your electrification projects at home or at work or wherever you are. And if you ever have questions about any of this material or other things in the electrification space, please don't hesitate to reach out to us. We'll try to get them answered if we can't answer them ourselves. And really appreciate you tuning in. Thank you.
Thanks, Christina. Thanks, Helen.
Thank you, everyone. Thanks for having us.
Thanks.
Thank you.